Hello there. In this video clip, we will be learning about the eigenvectors of a covariance matrix and what are the properties of those eigenvectors. So we start off with what's the decomposition of a covariance matrix. So according to spectral, it follows from the spectral theorem that every real symmetric matrix and the covariance matrix is an example of a real symmetric matrix. So all real symmetric matrices can be decomposed into three components: P, D and P transpose. So let's take a look at what these three are. Now the P can be written in this form, where the column vectors are all orthogonal unit vectors, which means that the ui uj and ui, and that should be ui transpose uj equals to 0, and ui transpose ui, and that's equal to 1. So ui transpose uj is equal to 0 for I not equal to j, and ui transpose ui is equal to 1. So the ui are orthogonal unit vectors, and the matrix D can be written, it's a purely diagonal matrix. As you can see here, your D is a purely diagonal matrix, and you will learn later that these lambda are your eigenvalues, and you will also learn that lambda I are greater than or equal to 0. And P transpose is just a transpose of your P. So all these arise as a result of, they follow from the spectral theorem. Spectral theorem is applicable to all real symmetric matrices, and because sigma is a real symmetric matrix, it can be decomposed in the following fashion. Now let's look at the properties of these ui, and it turns out that these ui are eigenvectors of sigma. So let's prove that. So if you do sigma uj, and now let me expand sigma, it can be written as PD P transpose uj, and from definition P is this matrix and D is this matrix, and P transpose and uj. Now let's look at these two, the ones on the right. So this is a row vector and this is a column vector, and you know that the ui uj, the product is 0 when I not equal to j. So all these terms get nullified except the term uj transpose that's somewhere in there. Okay, so you get just a column vector of this form with a single 1 and the rest of the elements 0. Now look at the terms on the left. So you have, and I've written this as a bunch of column vectors, and there's a diagonal matrix, and the rest of the entries here are all 0. So it turns out from the way these matrices are that lambda 1 chooses only u1, lambda 2 chooses only u2, and in general lambda I chooses only ui. So we end up with this matrix down here, and it's just a simple, you could work it out yourself, just a simple calculation, right? Just a simple simplification. So you end up getting lambda 1 mu 1, lambda 2 mu 2, and so on up to lambda d mu ud. and then when you multiply with this, you just get a singleton. It's not a singleton because uj is a vector. You just get lambda j uj. So sigma uj equals lambda j uj, meaning that uj is an eigenvector of sigma and lambda j is an eigenvalue of sigma. Now let's go on to the second property of these ui of these eigenvectors, as we have just proved. So it's true that ui transpose sigma uj is 0 for I not equal to j. So we already know that sigma uj is lambda j uj, sorry. So when we left multiply both the sides by ui transpose, so we get ui transpose sigma uj is equal to ui transpose lambda j uj. And now you know that matrices are, and vectors also, they are commutative with respect to scalar multiplication. So you can interchange these two and you get lambda j ui transpose uj. And you know that ui transpose uj is equal to 0 because these two are orthogonal unit vectors. So which means that this result is proved that ui transpose sigma uj is equal to 0. We will make use of this later, this particular result. And the third property of these eigenvectors is that when you project the data along these eigenvectors, which data? The data using which you have computed the covariance matrix. So if you project the data along these eigenvectors, then you get the projections along the two vectors, they are uncorrelated with each other. So let's take a look. Now I've drawn x1, x2, and actually these are not x1, x2. Let's call this d1 and d2, right? So these are d1 and d2. Okay, and these d1, d2 correspond to some two dimensions. Let's say the first two dimensions of the examples, the instances or the examples, the training examples. And you have a point x here, and u1, u2 are my eigenvectors. So when I project x along u1, see I drop a perpendicular, and this is the projection of my x along u1, u1 transpose x. Okay, and I told you that projection means that a dot product with a unit vector, and so u1 happens to be a unit vector, so it's the same. And you can also project x along the u2 direction, in which case you would get u2 transpose x. Okay, so these two are projections of x along the directions of the two eigenvectors u1 and u2. And it turns out that these, if you project all the data, the entire data set in the training data, if you project all the training examples along these two directions, you would find that the values obtained, the u1 and u2, they are uncorrelated. And let's prove that. So the projection of vector x along ij is ui transpose x, and it can also be written as x transpose ui. They are the same. And the same for the projection along uj. Okay, so when the entire data x is projected along ui, what happens? So you see that this is a row vector and this is a column vector. Always when you do a dot product, the first one's got to be a row vector and the second one has got to be a column vector. So in this case I've just projected x along ui, but now I want to project the entire data. So in order to project the entire data, I would need to take a product of ui transpose x transpose. So in x transpose, all the vectors x are in column vector format. So when I do that, I'll essentially be taking one row ui transpose and multiplying with the column vector, the first column vector, to get the first projection. Then I would multiply ui transpose with the second column vector to get the second projection, and so on. Okay, and the dimensions, let's just take a look at the dimensions. Ui transpose has dimensions 1 cross d, and x transpose has dimensions d cross m. So the multiplication is compatible, they're compatible for multiplication, and the resulting matrix will have dimensions 1 cross m. Okay, so basically the projections are all kept one after the other in a row matrix. Now, and similarly you can do the same for j. If you want to take the projections of x along j, you would just say uj transpose x transpose. Okay, and now we will compute the covariance between the two projections. You've already learnt in the previous clips that if you have two features fi and fj, then the way to take the covariance between them is by computing 1 by m into fi transpose fj, right? So where fi contains all the it contains the feature value I from all the examples, and fj contains the feature value j from all the examples. And the same is true here also. Only thing is you get from all the examples the projection along ui, and similarly you get for uj. Okay, so now this is a row vector, and so you just use this, and this is your projections along ui represented as a row vector. Now you need to take your projections along j, and you need a column vector, so you take the transpose and 1 by m. It's exactly of that form. So when you do that, and if you just use the result for taking the transpose of two matrices AB transpose equal to B transpose A transpose, right? So when you do that, when you take the transpose of this, you get x uj. Okay, we already know that multiplication is associative, right? So why not just multiply these two first, right? X transpose x, and when you do that, you get the matrix sigma, and this we have discussed in one of the previous video clips. So you end up getting ui transpose sigma uj, and you know that we just learnt that ui transpose sigma uj is equal to 0, meaning that the covariance of one feature with respect to the other feature, covariance of the projections along uj with respect to the projections along the covariance of the projections along ui with the projections along uj, the covariance is 0, and it means that the two are uncorrelated. So why do you think we are looking for uncorrelatedness? It's because uncorrelatedness is regarded as a weak form of independence of the features, right? And normally when you choose a set of features for classification, you would want uncorrelated set of features in order to get a better classification performance. So that is why we try to get uncorrelated set of features. And okay, and this is another thing that follows. Now supposing you take the correlation of the feature along the direction I with itself, meaning instead of the j you put an I here, and when you do expand it, you will end up getting ui transpose sigma ui. Okay, and see, ui transpose sigma ui is the same as lambda I. You know that it's very easy to prove that. You already know that sigma ui is equal to lambda I ui, right? Now you just left multiply by ui transpose to get this result. So ui transpose ui, it becomes identity matrix, it just becomes 1. Okay, so yeah, another thing that you should realize from here, this here is actually the variance of the data projected along ui. And you know that variance is always a positive quantity. And when you say that this is equal to lambda I, it means that lambda I is a positive quantity always, right? It follows that lambda I is always a positive quantity. Okay? So this is the end of this video clip regarding eigenvectors and properties of eigenvectors. I thank you very much.